Hey folks, and welcome to today's lecture. So last lecture we ended with a couple of complex mathematical functions that helped us describe what the wave function looked like for the particle on a sphere problem. And today's lecture is going to take a different type of potential, in fact one that's really near and dear to our hearts as chemists, hydrogen atom and things that look like hydrogen. But we're going to use a lot of the same mathematics that we used in last lecture to help us get to the point of describing hydrogen's wave function. And so if you need to, go ahead and quickly skim over the wave function that we came up with from last class so that you can follow along with today's discussion of deriving the wave function for hydrogen atom. There's a lot of good resources out there that go through the math, same math that we're going to go through today. Of the textbooks that you have at your disposal, I really like both Atkins and Griffith's treatment of the hydrogen atom. And if you happen to have an older edition of Atkins, I tend to like that one even better if you need some related reading. Okay, let's go ahead and get started. So, just like in all the problems that we've tackled so far in this class, describing the potential energy for hydrogen-like atoms is going to be our first step in solving for the wave function. Now, a hydrogen atom has two particles associated with it. One particle is the positively charged nucleus. Remember that hydrogen has one proton and 0 neutrons. And then also, a neutral hydrogen is going to have a negatively charged electron. We're going to expand our discussion just a bit to treat so-called hydrogen-like particles, simply because the math is going to be identical. So I'm going to add in an extra factor into all the math that we do today for Z, the atomic number. And that's just so that we can have an arbitrarily large nuclear charge, but still for today we're only going to tackle atoms that have one electron. And so here, just like in your GChem class, the letter Z represents the atomic number, and so the number of protons is given by Z, and so hence the total charge on the proton is positive ZE, where E is this constant called the elementary charge. And it has a value of 1.6 times 10 to the negative 19th coulombs. Our electron has a charge of negative E, where E is still that elementary charge. And so the potential for this atom is then going to be given by Coulomb's law. Coulomb's law, if you've forgotten from your physics class, states that the potential between two charged particles, we'll call them Q1 and Q2, is proportional to the product of those charges divided by a couple of different constants, 4 pi, E epsilon naught, which is the vacuum permittivity and has a value of 8.8 times 10 to the negative 12 Faradays per meter. And then also, Coulomb's law says that the potential is inversely proportional to R, the distance between the two particles. So in our case, our nucleus has a charge of positive ZE, our electron has a charge of negative E, and so that gives us a potential for these hydrogen-like particles of negative ZE squared divided by 4 pi epsilon naught R. Now, there's a couple things that I want to say about this potential that applies both to classical and quantum mechanics before we move on. The first thing I want to note is that this potential is negative. And what that means for us, especially considering that when would this potential be zero? The zero of energy is when our electron and our proton are infinitely far apart from one another. So as R approaches infinity, this potential goes to zero. So as the two particles come together, there's a lowering of energy, and that means that the proton and the electron are experiencing an attractive interaction. The second thing that's important is to note that the potential is proportional to Z, the atomic number of whatever our hydrogen-like atom is. What that means for us is that larger atoms have a stronger attractive interaction between the electron and the nucleus. And last but not least, as we kind of just went over, the potential is inversely proportional to R, so closer together means a stronger interaction, farther apart means a weaker interaction, until in the limit of infinite separation, these two particles experience no attractive or repulsive interaction with one another. And with that, we can now start to talk about the Hamiltonian for these hydrogen-like atoms. I want to say before we start off in this that what we're going to go through is a fair amount of math, both in terms of the algebra, as well as introducing a couple of new special functions, as well as thinking about some coordinate transforms that if you haven't taken multivariable calculus, may seem slightly new to you. If you're in that position, my goal is that you understand the general principle of how we're going through this derivation. Not necessarily in terms of every detail, but really my goal is for us to be able to see what the wave function looks like, where the quantum numbers that we learned in GChem come from, and allow us to see enough of the math that next lecture, when we start talking about some of the applications and implications of these hydrogen wave functions, that we can understand where some of this math came from in the first place. And so, going back to our slide here, the Hamiltonian for a system, remember the Hamiltonian operator is an operator that corresponds to the total energy of the system. What is total energy? Well, it's kinetic plus potential energy. And in this case, because we have two particles, we should consider the kinetic energy of both of those particles separately. So I'm going to have one term that describes my kinetic energy operator for the nucleus, and I'm going to use subscripts n, capital N, to describe that we're talking about the nucleus. I'm going to have a kinetic energy operator that describes what the electron is doing and its kinetic energy. I'm going to show that in yellow and give you the little subscript E to denote that we're talking about the electron. And then last but not least, we have a potential energy term, which is exactly what we discussed above. And so putting all those pieces together, we have that our Hamiltonian operator is negative Planck's constant squared divided by 2 times the mass of the nucleus times our del squared operator for n, just like we did on the particle and the sphere. Eventually we're going to have to start thinking about this del squared operator in terms of spherical coordinates, but we're not going to do that just yet. And then so that's our first term. The second term is negative h bar squared over 2 mass of the electron, in this case, del squared operator for the coordinates of the electron, and then minus ze squared over 4 pi epsilon naught r, which is exactly our potential that we defined for the hydrogen atom above. Now, I want us to think a little bit about this coordinate system because it's pretty complicated. In particular, we have to be consistent about what coordinate system we are using to describe this problem. And our potential energy is expressed in terms of what's called internal coordinates. That means it's trying to decide the relative position between the nucleus and the electron. And on my diagram, on this graph that I've shown to the bottom right, here I'm trying to depict our different types of coordinate systems you could use to describe the positions of these particles. And I'm using vector notation because all of these coordinates are three-dimensional. And so v of r is expressed in terms of this green vector, r, and in particular, since there's no orientational dependence, really it's just in terms of r, the variable. But up until this point, normally we've been doing all of our coordinates in terms of absolute coordinates, like what's the distance between some origin for my coordinate system and where one of my particles is placed. That's kind of what we did for the particle on a sphere. And in that case, we have to start thinking about absolute positions for each particle. So the absolute positions that would be for my red term would be given by this red vector. It's a vector pointing from the origin to wherever my nucleus is. And my yellow term is currently given in terms of this yellow vector. It's pointing from the origin to where my electron is. And wouldn't it be nice if instead of having 3 different kind of competing coordinate systems for these different particles, we could break this down a little bit more? The natural way in physics, it turns out, to break this coordinate system that's the red and yellow vectors describing all the positions of the different particles, again here I have 2 particles, nucleus and electron, in terms of absolute positions, and instead, what if we described how the center of mass is changing in terms of absolute coordinates? That would be that purple vector, and then as a second vector to describe the relative position between the 2 particles. So I could either talk about the problem in terms of red and yellow, or I can talk about it in terms of purple and green. And since I have the potential in terms of green right now, it's going to be easier for me to re-express these red and yellow terms in terms of this purple, or the purple and green arrows, rather than trying to do the reverse problem. So that's pretty technical, but we can do this coordinate transformation. And the way that we're going to describe this then is that the motion of the system is one piece is translational motion of the entire atom center of mass. Now, if you remember from GChem, a nucleus, or a single proton, is almost 2,000 times heavier than an electron. And so the center of mass for this particle is so close to just being the position of the nucleus and the mass of the nucleus. And so we have our purple term, but if it looks really close to you to the red term, it's because there's such a big difference between the relative weights of the nucleus and the electron. The next kinetic energy piece that we have to describe is the relative motion of the electron and the nucleus as related to one another. And so in this case, our Hamiltonian is transformed in terms of a Laplacian that depends on spherical coordinates, r, the distance between the electron and the nucleus, and sort of also the angular dependence, which our potential doesn't have any angular dependence, but truly you could think about this electron with respect to its position around the nucleus. And then your mass, in this case, gets transformed into a reduced mass. That reduced mass is very close in this case to the mass of the electron. So depending on which textbook you're reading, sometimes you'll see the entire derivation for the hydrogen atom in terms of mu, this reduced mass. Sometimes you'll see it just replacing mu with the mass of the electron. And that's what I'm going to do. Only in extremely precise applications of Schrödinger's equation would you ever need to know what the difference between mu and just the mass of the electron is. And so the Hamiltonian then, which we're actually going to start with for today, is the Hamiltonian that describes how the entire atom can translate in space, given by this purple term. So that would be a kinetic energy piece related to the entire motion of the atom. And then there's a second piece that relates to what we would call the electronic Hamiltonian. How is the electron moving with respect to the nucleus? And for that, there's both a kinetic energy piece, that negative h bar squared over 2 me times del squared operator, and there's also a potential energy piece, which is Coulomb's law. And typically, because this purple term is so close to being related to the motion and the mass of the nucleus, and the green terms are so close to being related to the motion and the mass of the electron, you'll see these referred to as the nuclear Hamiltonian and the electronic Hamiltonian. And I'm not going to go over this, but using separation of variables, kind of analogous to what we've seen thus far in this class, because our Hamiltonian can be split into terms that depend on one variable at a time, so no products of our nuclear coordinates times our electronic coordinates. Separation of variables works in this case, and our Hamiltonian, our overall Hamiltonian for the entire system, will be the wave function for the nucleus times the wave function for the electron. And the wave function for the nucleus is not actually that interesting in most cases, because it has a big enough mass that we don't necessarily need quantum mechanics to describe how an atom just moves around in space. We do need quantum mechanics to describe how the electron moves with respect to the nucleus. And so for today, really the equation that we're going to try and solve is the electronic wave function, the electronic Hamiltonian. And so here we have our thus far simple looking Hamiltonian that we're going to solve for today. And in keeping with my notation up until this point, I've put little subscripts to remind us that this wave function is just describing how the electron is moving with respect to the nucleus. The energy is just describing how the electron is related to the nucleus, but after this point, I'm going to drop those subscripts, and you're just going to see me start to talk about psi with the coordinates r, phi, and theta, where now we can understand that those are relative coordinates, or if you like, we're basically assuming that our nucleus is fixed at the origin and asking how the electron is positioned with respect to that nuclear origin and what the wave function looks like and how it changes as a function of those internal coordinates. And to start understanding why this is going to be complex mathematically, just like last time, we want to treat this problem in spherical coordinates because our potential is spherically symmetric. And that means our del squared operator is a complex blend of operators that relate to derivatives with respect to our angular coordinates and derivatives that are with respect to our radial coordinates. And a couple of tie-ins to last lecture. Remember that this little kind of witch hat looking operator is called our Legendre operator. That's what led us to our Legendre polynomials from last time. And unlike last lecture, now this electron is allowed to change its distance away from the nucleus. And so unfortunately, we can't drop these terms in our del squared operator that refer to derivatives with respect to the radius. And so how this problem is going to be more complicated then compared to our particle on a sphere problem is that now we have to do separation of variables to try and get a product wave function that depends on a radial component or a radial wave function and an angular component and an angular wave function. And so just like last time, this algebra is lengthy, and I'm going to try and color code it so that we can see once again how this separation of variables technique allows us to take terms which currently depend on products of things that depend on angles and things that depend on our radius and try and separate them out. And so where we're going to start, right now as you see it at the bottom of my screen, I have our complete Hamiltonian and my complete version of the time-independent Schrodinger equation in spherical coordinates, and I've plugged in our del squared operator and color-coded it so that you can see what in this equation depends on angular coordinates, what depends on radial coordinates. And so what seems really tempting to me at this moment is to say, well, let's just divide everything by r times y. And to rid myself of that temptation, because it would not actually be mathematically correct, the first thing I'm going to do is recognize that order of operations says you have to take all the derivatives before you can multiply or divide. And so my first step, in order to clean this up and make it more obvious what I'm allowed to multiply and divide by, or in other words, so I can make this seem that it will obey the commutative property, I'm going to take all of my radial wave function and apply it to each term inside my operator for my Legendre operator. And then I'll do the same thing to my angular wave function. So for the radial wave function, I'm going to go right to left. So my term closest to r with my Legendre operator, r can be taken outside of this term. So it can show up right here because I know that my Legendre operator is independent of the radial coordinate and only depends on my angular coordinate. And so I'm allowed to take r outside or to the left of this term. I need to leave the y to the right of this term because it's understood that I will then have to operate this Legendre operator onto whatever my y function is. Going for my second term, now for both this second and third term, these are functions that depend on radial derivatives, but are independent of angular coordinates. So here I'm going to take the y function to the left of each of these terms, and I'm going to leave my r functions here and here inside of the derivative as a way of reminding myself that I actually have to take the derivative of whatever the r function is with respect to r, and so I can't pull it all the way out to the left-hand side. And so now that we've done this, it's a little bit more clear to me where it is that I could divide or multiply by different functions in order to try one more time to play our game of let's get all the purple terms in one place and all the blue terms in another place. The best way to do this, as it so happens, is to multiply, or rather divide, both sides of the equation by capital R times capital Y, and then R to the -2. And so if we do that, my line that is of my derivation, that's right here, I'm going to divide everything by R, divide everything by Y, and then multiply by R squared. And once I do that, you can go ahead and pause the video for a second if you need to convince yourself that my first line leads to my second line. But really all that I'm doing is some algebra here to multiply both sides by R squared, divide by capital R, capital Y. Once I do that, this starts to look a little bit cleaner because now I have a function that is decoupling my purple and my blue terms. And then what I'm left over with is, let me go ahead and clean this up actually, I accidentally made it black. Once I rearrange these terms a little bit by subtracting off my term on the right hand side to really group all these purple terms together, I'm then left with a set of functions that on my left hand side I have a bunch of stuff that only depends on my capital or my R function, or on the variable R if you like better. And then on the right hand side I have a number of terms, or on the middle section I have a number of terms that just depend on my angular coordinates. And this is exactly what I wanted to happen in order to make sure that my separation of variables technique would work. Okay, I think I got all of my terms in purple that I needed this time around. Okay, and so just like last time, we can now say that because the terms in purple only depend on R and the terms in blue only depend on our angular coordinates, to make sure that the left-hand side is always equal to a constant, and in particular to make sure that it's always equal to 0, that means that this purple equation has to be equal to a positive constant, and the blue portion of my equation has to be equal to another constant that's equal in sign but opposite in magnitude. And you can choose any constant that you want, just like the letter C, but you can also be a little bit clever if you've already solved this equation before and make a clever choice of what to call your separation constant. And what I'm going to choose for my separation constant is h bar squared times L times the quantity L plus 1 divided by 2me, where yes, this L factor is an integer and it's that angular momentum coordinate that we talked about in last lecture. So if we choose this as our separation constant and we think about our angular equation a little bit more, you'll notice that my equation then becomes h bar squared over 2me times y times h bar squared times that L plus 1 divided by 2me, and a lot of these constants cancel out with each other, such that I end up with the equation, my Legendre operator times y is equal to a set of constants times the original y function. But wait a minute, this looks vaguely familiar from when we did the particle in a sphere. And in fact, our particle in a sphere problem as a recap is shown in the purple text. It said that for a choice of energy, E is equal to L times L plus 1 h bar squared over 2I. I was that in that moment of inertia from before. That the wave functions that fit this equation are the spherical harmonics, which depended on two quantum numbers, L and m sub L. And plugging in this value for E that we found from last lecture, we can simplify our equation down to say that the solutions to the equation Legendre operator times a wave function is equal to negative L times L plus 1 times that spherical harmonic wave function again. And this is identical to the equation that we're trying to solve for in this very moment. And so that means we can take a deep breath and say we actually don't need to think anymore about this angular equation. The wave functions that we're looking for that obey our angular wave function are the spherical harmonics, because the form of the equation is the exact same form that we had when we tackled that particle on a sphere problem. And so that seems really great for us because, one, now we know that it's no coincidence that last lecture we used the variables L and m sub L to describe the particle on a sphere quantum numbers. Those are our quantum numbers for the hydrogen atom that we learned about in GChem. And two, it means that we now know that the hydrogen wave functions, they aren't themselves the spherical harmonics, but they are the spherical harmonics multiplied by some radially dependent wave function. And so the last question that we need to answer for today is, well, what is that wave function? So let's go ahead and solve for the radial wave function. So reprinted from above, the radial equation, once we know that our separation constant is this kind of wonky negative L plus 1 h bar squared over 2me term, we can set our right-hand side equal to the separation constant, and our left-hand side we can set identically to what it was up here in our derivation, in kind of the top of my slide right now, where I said what is the portion of our Hamiltonian, or our time-independent Schrodinger equation, that just depends on R. And so what I want us to do is to think deeply about what some of these terms mean in my radial expression, or my radial equation that I'm going to try and solve for, and then we'll follow up by introducing what those equations are. And so the two terms that I have in this function, one is a term that conceptually relates to the kinetic energy that results from radial motion. And so as the electron and the nucleus kind of come together, come apart, there's going to be, depending on how fast that motion occurs, a kinetic energy term associated with that. And that's what our first term in our radial time-independent Schrodinger equation refers to. The second term is what a lot of people refer to as an effective potential. Part of this effective potential looks really familiar. It's the attractive Coulombic energy that we introduced at the beginning of the lecture. But now, all of a sudden, in part because we needed a separation constant to relate to the angular wave function, a new term has shown up that depends not on our inverse, but our squared inverse. And what we've taken to call this energy and how we conceptually relate it or think about it intuitively is that this is a term that arises from centrifugal force. So as our electron is rotating around the nucleus, there is a force that's exerted as it rotates around. It's due to the angular momentum of the electron circling around the nucleus. So we call this term a centrifugal energy term, and notice that because the term is positive, that means that this is a repulsive contribution to the effective potential that this electron experiences in a nucleus. Now, close to the nucleus, the centrifugal term is going to dominate because the r squared term matters more and more, gets bigger and bigger as r goes close to 0. Far away from the nucleus, in kind of this asymptotic regime, not all the way out at r equals infinity, but kind of at long-ish r distances, we see that the Coulombic term is going to dominate. Because as r gets big, this r squared term goes to 0 pretty quickly, and so it's this 1 over r term that becomes important. And if we go ahead and take a little bit of time to plot this function, then you can go ahead and see exactly that kind of close to the nucleus and farther away from the nucleus behavior. And so before I talk about the behavior too much, I want to highlight two orange comments that relate to interpreting the axes of these graphs. And both of these are ways of us saying, you know, there's a lot of constants that are showing up in this problem. Maybe we could lump these together and call this a unit system. In fact, these are two of the fundamental constants, or groups of constants, that are going to define in so-called atomic units what does distance look like and what does energy look like, in ways that help us avoid having to write many, many groupings of constants together. So on our x-axis, we're going to introduce a term called A naught, or A sub 0. This is our Bohr radius, same Bohr as the Bohr model. And A naught is defined as a whole bunch of constants that we've introduced in today's lecture. 4 pi epsilon naught h bar squared over the mass of the electron times the elementary charge squared. That's not that interesting to remember. What I do remember is that a Bohr is about half an angstrom. And so angstroms, remember, like an oxygen-hydrogen bond distance in water is almost exactly 1 angstrom. So as you're looking at the x-axis of this graph, I want you to kind of orient yourself to saying, okay, these functions, I've plotted r over the Bohr length, so I've plotted 14 Bohr lengths. And what that means is that at 14 Bohr lengths, or 7-ish angstroms, all of my functions are mostly looking just like a Coulomb's law term. This 1 over r squared term isn't that important, and all the functions are going to converge to the same point if we went farther and farther away from the nucleus. At short distances, and I would even say at chemically relevant distances of 1 to 2 angstrom, we see that this r squared term is dominating for any function where L is not equal to 0. You'll notice, and kind of sneakily from the math above, that if L is equal to 0, this centrifugal energy term goes to 0. And so that's why our L equals 0 term doesn't seem to have any repulsive contribution to it. In terms of our energy scale, I'm going to introduce a new unit system, or a new unit of energy called the Hartree. And the Hartree is, once again, a bunch of constants that we've seen in today's problem multiplied by each other together. And it's a very small amount of joules per particle, or if you want to talk about a mole of energy, then this would be equal to 2,625.5 kilojoules per mole. And so we're going to start to see these ways of expressing energy show up a couple times in this course. In fact, these numbers are personally very familiar to me because I'm a quantum chemist, and so I often am more comfortable thinking in Hartrees actually than I am in kilojoules per mole at this point. But it's helpful to plot things in terms of these unit systems because it helps us see the essential behavior of the functions without getting bogged down in the constants. And it also helps us see where these functions have kind of turnover behavior. And so now that we've gotten our axes out of the way, we can talk a little bit more about what we see in these plots. And the two things that I want us to notice is, one, that all of these functions asymptotically decay to 0 for any value of L. And that, two, as L increases, we see that this repulsive behavior starts to occur at larger and larger distances. So our minimum energy, where V effective is at a minimum, is pretty close to the nucleus for L equals 1, and it's increasingly far away from the nucleus as we increase L. And what that means for us, because soon we're going to be remembering from general chemistry that L equals 0 corresponds to an s-type orbital, L equals 1 is a p orbital, L equals 2 is a d orbital, that this means that p and d orbitals are going to have a repulsive energy close to the nucleus, which means that their probable locations for an electron in a p or a d orbital is, because of this effective potential, going to also be shifted farther away from a nucleus. An electron in an s orbital has no problem being right next to the nucleus because there's nothing in the potential that repels it away, but an electron in a p or a d orbital does have that repulsive behavior, and that's going to change the shape of our wave function as a result. Okay, so we talked a little bit about the potential that defines our radial wave function, but we haven't actually solved for the radial wave function yet. And just like we did with the spherical harmonics, it turns out that there is a special set of functions that defines the solutions to the radial wave function for the hydrogen atom. You would be forgiven for lamenting the fact that this is also going to be a special set of functions called by some L name. In this case, it's the Legere polynomials, not Legendre, not Lagrangian, but Legere polynomials. And just like we did with the spherical harmonics, let me go ahead and give you a table of values for the first couple of these Legere polynomials, so that you can see in practice that even though the abstract version of this equation looks somewhat complicated, the actual polynomials themselves aren't too bad for small values of n and L. And so a couple of things that I want to point out about these solutions to the radial equation. One, there's a normalization constant showing up, necessary but not super interesting to us at this point in the course. Two, I have taken the liberty of grouping together my constants that always show up around r. In fact, it's this 2 zeta, zeta being the atomic number, times r divided by a naught, the Bohr radius. And I'm going to call that rho, just to simplify these expressions a little bit. But in your head, you can say rho and r are proportional to each other. So they're describing the same concept of how far away is the electron from the nucleus. And we see in these radial wave functions that our radial wave function has a term that depends on r raised to the power of L. That is going to help us define what happens, what does the shape of this wave function look like for small values of r or small values of rho. Then there's this Legere polynomial, which kind of links together what the behavior of the radial wave function should look like close to the nucleus versus far away from the nucleus. And then we have a decaying exponential term, which is going to govern the behavior of the function in a limit where this function is at bigger values of r. And so you're going to get a chance in class to plot some of these radial wave functions, but the only thing that I want to point out at this point is how this relates to the existence of quantum numbers. In particular, our quantum numbers that show up in the radial part of our wave function are n and L. So L is a repeat from the spherical harmonics, but n is new. We're going to call n our principal quantum number, and I want you to notice that unlike the particle in a sphere, where there were no restrictions on L aside from it being an integer, that in the hydrogen atom we have an additional restriction on L. And that is the fact that there are no Legere polynomials for which L is equal to or bigger than n. And so if you remember from GChem, our restriction that L be smaller than n is directly related to these Legere polynomials and which ones actually exist. So n is going to, by definition of how these Legere polynomials work, be a positive integer. So n equals 0 is not okay. N equals 1 is our smallest value of n that's allowed. And L has to just be a non-negative integer. So L equals 0 is just fine. L equals 2 is sometimes fine, but the first time L equals 2 is going to show up is when n is equal to 3. And so what I really like about this table that I'm showing you right now is it maps out for us what types of orbitals depend on which combinations of n and L. And it helps us to see, just like you saw in GChem, that a 1s orbital is just fine. But why is there no 1p orbital? Because there is no Legere polynomial that's associated with something that we would call a 1p orbital. N equals 1, L equals 1 is just not a combination that's allowed. And so since it's not an allowed wave function, that means that it's not an orbital that you'd be introduced to in a general chemistry course. And I have to say, I just find that really neat, that we did have to go through a lot of math to get to this point today, but suddenly, something that felt like a bunch of arbitrary rules in GChem, there are no 1s orbital, or no 1p orbitals, but there are 2p orbitals. But you can't have these different combinations of quantum numbers. Now we can start to see through the math that these are all naturally arising quantum numbers and allowable orbitals based on the solutions to Schrödinger's equation. And so with that, let's go ahead and put this all together to end off our lecture. we wanted to solve at the beginning of the lecture for our hydrogen or our hydrogen-like atom's wave function. And through separation of variables, we learned that that is a product of a radially dependent wave function times an angularly dependent wave function. And so putting this all together, we see that our overall hydrogen atom orbitals look like spherical harmonics times, depending on what n and L looks like, polynomials that decay exponentially in the long range behavior, but in the short range maybe kind of have some squiggles or some polynomial-like behavior to them. And thus far, we have identified the existence of 3 different quantum numbers. So thus far in our hydrogen atom exploration, we have n, our principal quantum number, which can take on values of 1, 2, or 3. L, our orbital angular momentum quantum number, which can take on values depending, once you've set your value of n, can be anywhere between 0 and n minus 1. And last but not least, our magnetic quantum number, m sub L. And once you've set your value of L, m sub L can take on any values that you like between negative L and positive L. The first few solutions to my overall hydrogen wave function are tabulated below. You can see that what I need to tabulate is that there's a different associated wave function for each unique combination of n, L, and m sub L. And then the other thing that I want to leave us with, before I leave us with some energy descriptions, I do want to give us just one sneak peek of what these hydrogen atom wave functions look like. And so there's a nice applet that I'll post on Moodle for this, but the same functions that I tabulated on the previous slide are what you can see in this hydrogenic atom viewer. Here is our s orbital. You can see I'm rotating around right now, which you can't see in the function because it's radially symmetric, but you can see in the little coordinate axes that are closer to the middle of the screen. So here's what our s orbital looks like. These are really just plotting the math of the wave functions that I've shown on the previous slide. And when we increase our values of either n or L, or maybe m sub L in some cases, we'll start to see that these orbitals look similar to what you saw in GChem, but maybe there's a little bit more complexity underlying the surface that we're going to have to tackle. So the function that I'm showing right now is my 2s orbital, and it still looks like an overall shape of an s orbital like you saw in GChem, but notice that there's 2 different colors showing up. And in particular, the way that this little applet works is it's giving you a red color anywhere the wave function is positive, and a blue color anywhere the wave function is negative. And then the brightness of the color relates to how positive or how negative is the wave function. And so this is one way of showing that the 2s orbital has positive and negative components to the wave function, and there's a small region close to the nucleus where it's negative, or where it's positive, and a much bigger, more diffuse region outside, farther away from the nucleus, where it's negative. We can also plot our p orbitals, and we have one set of p orbitals that is aligned with the z-axis, that you might even call the pz orbital. One set of orbitals that is aligned, I'm going to use my real orbitals. One set of orbitals that is aligned along the x-axis, and one set of p orbitals that's aligned along the y-axis. And so once again, we see hopefully this connection between our GChem orbitals and the actual mathematical versions of the wave functions that we've been introduced to in today's lecture. And now that is only a sneak peek. We're going to talk a lot more in the upcoming lectures about how to visualize and understand what these visualizations of the wave functions look like. But the last thing that I want to leave us with today is the function that describes the energy of any wave function. What's its corresponding energy? And what's really interesting is that for the hydrogen atom, and it turns out only for the hydrogen atom, the energy only depends on n, the principal quantum number. And so all of the expression, I've given you a couple different ways of thinking about the energy. You can use whichever version you like best. The first version I gave to you in terms of all of the constants that showed up in today's lecture. The big thing to notice is that the energy of the orbital is inversely proportional to n squared. If you like, you can also say that the energy of the nth orbital is half of a Hartree times whatever 1 over n squared is. Or if you really want to put this in terms of raw numbers and SI units, you can see that the energy of the orbital is inversely proportional to n still, but times 2-ish to the times 10 to the negative 18th joules. Okay, and so in today's lecture video, I hope that I began to answer some of our questions. What is the wave function for hydrogen? What are its energies? But I'm also secretly hoping that I've also raised a lot of questions in your mind. The first question should be a sort of lingering confusion about the connection between the mathematical expressions for the wave function and the plots that you've seen either in GChem or that I gave you a little sneak preview of at the end of today's lecture. We need to talk more, and we will talk more in next lecture, about what it looks like to visualize these H-atom wave functions. A second question that I hope that you don't yet have resolved in your mind is the so what question. Just like we did in Particle in a Box, it was one thing to introduce the physics of what the particle in a box was, and it was a very different thing to talk about how that related to us being able to understand light emission and absorption in something like a quantum dot. We're going to have to do the same thing with a hydrogen atom wave function and talk about applications and implications of what we've derived in today's lecture. I hope that you haven't forgotten about our fourth quantum number, m sub s, our magnetic spin quantum number, but we didn't see m sub s show up in today's lecture. And so what about m sub s? We won't tackle that next lecture, but 2 lectures from now, we're going to talk about that quantity. And then last but not least, I hope that you are interested in atoms that go beyond hydrogen and go beyond just other atoms with higher atomic numbers, but still limited to 1 electron in total. And so what about electrons, or what about other elements on the periodic table? What about neutral carbon or neutral neon? What do those wave functions look like? And so that is going to be the subjects for our next 2 lectures. And until then, I look forward to seeing you all in class, hopefully with many questions. And I hope that you've been able to appreciate that even though there's a lot of complex math in this, that it's actually still really beautiful. We're able to show that our hydrogen atom has and obeys the Schrodinger equation just like the other problems we've tackled in this lecture series. And in fact, all of our familiar results from GChem now have a strong theoretical and fundamental background. So with that, I look forward to seeing you all in class.